Hi, this video will be mostly focused on the blocking strategy as one of the most important basic principles of experimental design. This video I will cover a little bit about the basic principles of experimental design, where blocking is one of these. And then I will talk about what is blocking, why we use blocking, how to block in two-level factorial designs. If we start by looking at the basic principles of experimental design, you can find more information about these in the first chapter of the course book. Randomization, blocking, and replication. Randomization is a fundamental principle within experimental design. We randomize to distribute the effect of noise factors more evenly and in a random way among the design runs. Blocking is a technique to increase the precision in effect estimates. It's a way of cleaning or taking out the effect of known disturbances or noise factors, such as different raw materials, different days of experimentation, personnel, etc. Take this out from the effect estimates so that they are not affected. Replication is important to have true replication of experimental design runs. It makes it possible to estimate the noise or the pure error in the experiment and makes it possible to use analysis methods that are not reliant on partly subjective methods, such as the normal probability plot of estimated effects. With a pure error estimate or true replication, we can go directly into the ANOVA and look at the p-values, for example, which is less subjective. Randomization, if we start about talking about that principle a little bit. So why is randomization important? Well, the impact of disturbances, noise factors are reduced, such as technical noise factors, machine wear, variation in voltages, variation in ambient temperature, and so on. We can also have organizational noise factors, such as the need to change operators and shifts and laboratory staff and so on during the experiment. We can also reduce the impact of erroneous factor settings, since in randomized designs, we make more frequent changes of the factor settings than in non-randomized designs. So erroneous factor setting is normally affecting fewer of the design runs in a randomized design. Randomization can also be a problem, of course, because not all factors are easy to change, frequently especially. It can also make it somewhat more difficult to keep track of the run order and make sure that all the factor settings are in the correct way in each run. Random error is also distributed on all effects that we need to be aware of that in the randomized run order. Okay, so more about randomization. Um, when and when perhaps not to randomize. So first, if a randomized run order only makes the experiment a little bit more complicated, we should randomize. If it is very difficult or even impossible to randomize, and we honestly believe that the process and the results will not be affected or disturbed by a non-randomized run order, then we can run the experiment without randomization. But this is perhaps quite unusual that we can make such an assumption. If you cannot randomize and you think the process is unstable and the results will be affected by a non-randomized run order, then we should of course try to work with stabilizing the process. A compromise that we should consider is of course the split plot designs, and we will come into this later on in the course. Okay, blocking. When should we do blocking? Well, when it's impossible to run all experimental design runs under homogeneous conditions, and when we know the noise factor and it can be controlled, we know which design runs will be affected and so on. For example, if we have one batch of the raw material that we need for the experiment and that this only covers perhaps let's say half of the experimental runs, then we know that we need to change the raw material in the middle of the experiment, and this can be a situation when we want to run the experiment in 2 blocks, for example. Why do we block? Well, if we know beforehand that a disturbance will occur, we can try to design the experiment in such a way that the disturbance will not affect the effect estimates. And by this, we increase the precision in the effect estimates. The basic idea of blocking is that we first choose an interaction effect, normally a higher order interaction, that will be allied, or in Swedish överlagrat, with the block effect. And this interaction, or these interactions, will be lost to blocks. For two-level factorial designs, this idea means that we can run the experiment in 2, 4, 8, 16, and so on, a number of blocks. So I will illustrate this idea with a very simple example. So we take the 2 to the 2 design, a two-level factorial design in 2 factors, and we want to run it in 2 blocks. So this idea means that we take the highest order interaction available. In this case, we only have the AB interaction. This is sort of sacrificed to blocks. So let's say we choose when the AB interaction has a plus sign in the matrix, we choose to allocate this run to block number 1. And when we have a minus sign, we choose block number 2. So that's quite an easy way of picking the blocks. However, we should note that when we calculate the effects A and B, there are equal number of plus and minus signs in front of each block, as you can see here. For the A, we have minus, plus, so we have minus 1, plus 2, and minus 2. So this sum of the block effect on the effect estimates A and B will become 0. So the A and B effects are not affected by a potential block effect. However, the AB interaction is completely confounded with the potential block effect. So we cannot separate the block effect from any AB interaction effect. So that is what we lose in this strategy. Here is a symbol of the which design runs we allocate to different blocks. The red ones are the block number 1 and the green ones are block number 2. Okay, so let's take a look at the 2 to the 3 design in 2 blocks. The same idea, so we choose the highest order interaction term available, ABC here. When ABC has a minus sign, we allocate, in this case, run number 1 in the standard order to block 1. When we have a plus sign, this is a block 2, and so on. So that's it's quite easy to allocate the blocks when you only have 2 blocks. Okay, so what about the situation with 4 blocks for the 2 to the 3 design? Well, we need to pick 2 interaction effects to become confounded by blocks, AB and AC in this case, and we can call these 2 block generators. We then need to determine the generalized interaction between AB and AC. We multiply AB and AC together, we get A squared BC is equal to IBC is equal to BC. So also the BC interaction will be lost to blocks or confounded with blocks. The division of the design runs between the blocks becomes then when we only have the plus signs, plus in this case, AB, AC, BC is plus, this is block number 4. Minus, plus is block number 1, and we can see then when this is repeated, minus, plus here, this is block number 1 as well. So the allocation of the runs to different blocks is determined by these combinations of plus and minus signs that are available to us. And there are 4 combinations. Okay. So in summary, here you have a table with recommended block generators for 2-level factorial designs. So we have number of factors, we have number of blocks we need to use, how many runs in each block, and we have the recommended block generator. And these are not mandatory, but these are the recommended ones. And we also see the interactions that we lose to blocks or that become confounded with blocks. So in this case, when we only have one block generator, we only have one interaction lost to blocks. When we have two block generators, we have three interactions lost to blocks. And when we have three block generators, as in the case with 8 blocks, we lose 1, 2, 3, 4, 5, 6, 7 interaction effects to blocks. You can see this table as well in your course book. Okay, so in summary, some important things in this video. Which are the basic principles of experimental design? Well, these are randomization, blocking and replication. We also need to know when and why blocking is a useful strategy. And we also need to know how to create blocks in two-level factorial designs. And with that, I thank you so much for listening, and good luck with creating your blocked two-level factorial designs. Thank you for listening. Bye-bye.